Hello friends, hope you find this video in a stress-free and healthy condition. In this we will learn the spring combinations, that is springs in series and parallel combinations, their basic need, how to evaluate the spring rates and the concentric springs. We'll see these two factors. So springs in series and parallel combinations. Now before moving on to the actual part of analysis, we will see why or what are the objectives behind the series and parallel combinations. The objective first is to save the area, that is naturally to save the space. Second, to change the rate of the spring at certain deflection, that is to accommodate more load in small space to provide a fail-safe design. This would be the third objective. Then we see this diagram, that is in which springs are connected in series. So figure shows two springs that are connected in series with the spring rates, that is individual stiffnesses, as K1 and K2. For this combination, actually the spring force, the force acting on each spring is equal. The force acting on each spring is same and equal to the external force. That means P will act on K1, P will act on K2, and the total deflection is the sum of individual deflections of springs, that is delta 1 and delta 2. So total deflection is delta 1 plus delta 2 as given here, that is total deflection is delta and delta 1 plus delta 2, where delta 1 and delta 2 are the deflections of two springs. We actually know that delta is nothing but P by K. Hence, delta 1 is equals to P by K1 and delta 2 is equals to P by K2. Using this in first, that is A equation, we will get capital P by K is equals to P by K1 plus P by K2. So taking out the load, we will find out the combined stiffness as 1 upon K is equals to 1 upon K1 plus 1 upon K2. So this is the stiffness for springs in series. Now we will see the stiffness for springs in parallel connection. So this figure shows springs in parallel connections. This is K1, stiffness for spring 1, and K2, that is stiffness for spring 2. So from this figure we have the force acting on the spring combination is the sum of forces of individual springs, and the deflection of individual springs is same and equal to the deflection of combination. So P will be distributed as P1 in spring 1 having stiffness or a rate as K1 and P2 in K2. So P is equals to P1 plus P2, but as we know P is equals to K delta, hence K delta is equals to K1 delta plus K2 delta. Therefore K is equals to K1 plus K2 is the stiffness of springs connected in parallel combination. So we can see this is say a single spring, this is a combination of springs in series, we can see, and this is the combination of springs in parallel. Okay. Now we will see concentric helical, which is also called as nested spring. So by the word meaning nested, it is a loop spring. Okay, so it consists of two helical compression springs which are one inside other having same axis. Naturally there will be two different diameters, inner and outer. In general there are two springs. However, in certain applications it consists of three coaxial springs, namely inner, middle and outer. If the outer spring has right hand helix, the inner spring always has left hand helix and vice versa. Adjacent springs generally have opposite hand to prevent the locking of coils. We observe these diagrams. Here capital D1 is the mean coil diameter of outer spring and capital D2 is the mean coil diameter of inner spring. Corresponding to D1 we have small d1, that is wire diameter of outer spring, and capital D2 we will have small d2, that is wire diameter of inner spring. C is nothing but clearance between the outer and inner. Again L1 and L2 are the lengths. We will see these parameters and how to evaluate them. So this is one practical example of nested spring. We see 3 springs inside each other. Now advantages of such combination is that we can design a spring with increased load carrying capacity in a restricted space. Okay, operation of the mechanism continues if sometimes one of the spring fails or breaks. This is actually resulting into fail-safe design. The spring vibration, which is called as surge, is eliminated. We will see this surge in later session. Such springs, that is nested springs, are used as wall springs in heavy duty diesel engines, aircraft engines and railroad suspensions. Governors of variable speed engines to account for fluctuating centrifugal force. Now we will see the relations, that is the dimensional analysis. Radial clearance between the two springs is given as C is equals to small d1 minus d2 divided by 2. So referring to figure, we will simply substitute the relation, that is capital D1 minus small d1 divided by 2 minus capital D1 plus capital D2 plus small d2 divided by 2. Rearranging, we know that C is equals to capital D1 minus d2 by 2 plus d1 plus d2 by 2. Therefore, we will get d1 as capital D1 minus d2 by 2. However, we know that the spring index capital C is capital D by small d. So using capital D is equals to C into D, that is d1 is equals to C into d1 and d2 is equals to C into d2. We will get d1 is equals to C d1 minus C d2 is equals to 2d1 and C 2d1 is equals to C into d1 minus C into d2, whereas d1 by d2 is equals to C divided by C minus 2 is used for the design of concentric springs.